Thank you very much for coming and joining online for the 137th NIA CFD seminar. Today's speaker is Vishal Srivastava. He had bachelor in aerospace engineering from Indian Institute of Technology in Kanpur, and he finished his PhD at the University of Michigan in 2022. And he joined NIA for a year, and then he's now at Analytical Mechanics Associates. But basically, over the last 3 years, he's been working at NASA Langley on this machine learning study. And he's going to tell us today about the data-driven improvements in Brown's predictions for reattachment of separated fluids. Please take over.
Thank you. So good morning. I'm going to talk on data-driven improvements in Brown's predictions for the attachment of separated fluids.
And please ask questions during the talk. I always forget to say this.
I did this work in collaboration with Dr. Chris Rumsey, Dr. Gary Pullman here, and Dr. Lee Wang at NASA Langley Research Center. So let's get started with the motivation for this work. So we know that Brown's models often will predict lengths of separation bubbles, especially for fluids that exhibit smooth body separation. Now, data-driven model augmentation techniques that have been introduced in the past decade could improve this predictive accuracy, and that was our hope going ahead with this work to see if we could improve such reattachment predictions. The main challenges as far as the data-driven model augmentation goes is do no harm. That is to say that any data-driven model augmentation should not adversely affect the model performance of the baseline model itself. And in addition to that, we have a challenge of generalizability, which in essence means that if we train or if we calibrate our data-driven model on one or two different flows, then those benefits should generalize to a variety of different fluids that exhibit similar physical phenomena. All right, so basically what we started with was the field inversion machine learning framework. And essentially, the first step in this framework for model augmentation is to introduce a correction term within the model equations. So basically, you introduce some kind of function within the model equations. This function will be the augmentation function. It'll take its inputs as what we call features. These are some flow quantities which are known to the model. And then it outputs a numerical value, which is the model correction. So you can think of this like some kind of function sitting within the turbulence model. All right, so the first step to infer this augmentation function is to infer the values of the model correction themselves as a spatial field for a given flow using this field inversion technique. It's just solving an inverse problem, which is essentially an optimization problem. So basically, you get a field of model corrections. The next step is to design appropriate non-dimensional Galilean invariant features such that we can pose an inverse problem to infer what the augmentation function should look like given the model correction and given our chosen features. So the step 4 is exactly that. We express the augmentation function as with a predefined functional form containing some parameters, and then we want to optimize those parameters such that we get this feature to model correction map accurately. Yeah. And so basically, the last step is just the inference of those parameters. All right. Now, the most critical aspect or the most critical part of this methodology is essentially the design of these appropriate features, because, as I'll show in the following slides, feature design is more or less human dependent in the sense that it cannot be automated as of now. And there are so many different permutation and combinations of flow quantities that it's better to have a human intuition there rather than getting it done by machine. Okay, so the augmentation that I'll show here was calibrated mainly on the NASA 2D wall-mounted hump flow. The mesh can be seen in the top figure, and then the results from the SST model and the SA model are shown in the bottom figure with respect to the experiments. Now, as you can see, both the SA model and the SST model, they overpredict the separation bubble, the length of the separation bubble. And the main reason for that is because within the separated region, the Reynolds stress within the separated shear layer is not as high as it should be. So another point to note here, by the way, is that both these models predict the skin friction behavior more or less accurately for some part of the flow right after separation occurs. So this is the part that I'm talking about, if you can see my laser pointer. And finally, the SST model shows a better skin friction recovery compared to the SA model.
Vishal.
Yeah.
My typical question I always ask.
Yeah. Yeah.
So this curve for SST and SA, are they well converged, like
Yes.
iteratively and grid converged?
Yeah.
So that it's all checked and verified.
Right. So these results are on the finest meshes from the TMR website, either the finest or the second from the finest, and they are properly converged.
Okay, but like even within your own computation, not relying on something external, so that you can show you can converge to zero residual, whatever small residuals you have, and then you can show that when you do grid convergence, so that your data converge to this curve.
For this particular flow, yes.
Okay.
For this particular flow, I did check that. So using my own flow solver, it did converge to very small values in terms of residuals, less than 1 minus 10, if I remember correctly.
Yes.
And it converged to this more or less this same plot, essentially.
So we can trust that this is basically solution to SA model and to SST model.
Okay. Yeah. And also, like the same results are found in several other papers in the literature also for data-driven modeling of separated fusions.
Because it's so difficult to verify and to make sure that
That's
something is true, so that like I'm often more relied on results that I
Right. But I did check that. Yeah. For this particular flow, I checked that.
Okay, thank you. Sorry.
No, that's perfectly fine. All right. So basically, the first step of the model augmentation process, as I illustrated before, is basically introducing a model augmentation term. In this case, we have the Spalart-Allmaras model, and we introduce a model augmentation term beta right here. Right now, beta is just a function of the spatial variables x, because we are going to do the field inversion, which gives you only a spatial field, not an augmentation function. The way we solve for the optimal value of beta is by solving an optimization problem where you minimize a cost function with a regularization function added to it. Lambda is essentially the regularization parameter. And the cost function is nothing but the discrepancy between the predicted values of the skin friction given a given field of beta values and the data associated with the skin friction from the experiments or high fidelity simulations. The regularization function is just a trigonode regularization. What that essentially means is that my beta stays as close to the baseline value of 1 as possible. So basically, if you substitute 1 here, you get your baseline SA model back. So that's what it does. Now, this field inversion technique was applied to the 2D wall-mounted hump flow case by Dr. Li Wang, and this is essentially the optimal solution that we get for beta. The way this problem was solved was using steepest gradient descent. I think later on we also explored something like LBFGS, but that also more or less gives similar kind of answers. And the sensitivities with respect to the inadequacy field are obtained by the method of adjoints, which essentially helps in this derivative-driven or gradient-based optimization. Now, in this field that you see below, you can identify 3 regions as a high beta region, a low beta region, and a high beta region again. We found that the third region is the most important in terms of getting the reattachment location correct. So that is what we started focusing on. So what we did then was,
Vishal,
yes,
so this distribution is the result of the optimization program?
yes, this is the result of the field inversion problem. So
And what was the data?
so the data was the experimental data for
Experiments.
yeah.
Okay. This result computed on finest grain, right? So that I guess that
These are the finest of it, the finest.
so if you change the green, the results stay the same. This adjoint or this beta stay the same.
So I haven't checked that, but I suspect it should remain the same as long as the way this problem is posed remains the same. Now what you should know here, that there's an even bigger elephant in the room than you're pointing to. The problem with field inversion is that it's not guaranteed to be unique because it by its very nature is still post, right? So if I just change this regularization parameter, right, lambda, the field might change quite a bit, right? If I change what my regularization function is, the field might change quite a bit. There are several things. Now, you may then say that, well, how do I trust what you're doing is correct, right?
There are some formal requirements. We can talk of this.
Right.
There are some formal requirements that could be satisfied. And for example, for this problem, dual consistency will be critical so that you want to ensure that you can converge both forward analysis and adjoint analysis to the limit. And okay, yeah, we'll talk.
Okay, yeah. But I think as long as these, the way this problem is posed, as long as that remains consistent, then I don't think there should be much difference between different grids. That is what I think I may be wrong. Okay. All right. So once we had identified that, well, we want to get this region modeled correctly, what we said was, okay, let's find a feature that kind of matches this region as closely as possible. Because what we want to do is we want to implement our augmentation only in this region and nowhere else, right? We don't want to touch anything else. So we use the vorticity Reynolds number and the turbulence Reynolds number. And basically, the first feature candidate that we tried out was this RE omega RET squared, right? And as you can see, the feature resembles very closely with the target that we want to achieve. So basically, as of now, as for feature selection, we are using the results from field inversion to give us a hint of what we want to do. Okay, so once we took this feature and we thought that, okay, let's just train an augmentation function using machine learning. And we did that. And basically what we saw was that for the hump case, the 2D wall mounted hump case, we found that the results improved. But for other cases, there was no change at all. And basically what we've understood from this exercise was that there was a clear Reynolds number dependence, and that a third quantity or a third Reynolds number was needed to generalize to different flows. Now, at this point in time, my analysis was that, well, there's nothing else in the Spalart-Allmaras model that can give me a new Reynolds number, and that the vorticity Reynolds number and the strain rate Reynolds number are more or less the same. So we need something which has two scalars, a turbulence model that has two scalars. So we went to the SST K-omega model, and there what we did was we used the turbulence kinetic energy Reynolds number, which is shown here. And then we also added a limiter to activate the augmentation only in turbulent regions. So what this limiter does is it activates only when the turbulence Reynolds number is greater than 10 and does not activate if it is less than 10. Then we did some trial and error, and we converged to kind of this kind of a functional form for our feature. There is pure trial and error, trying out different exponents, trying out different things, and that is what we reached on. Once we reached at this feature, what we found was that the augmentation need not be a very complex function of this feature. This feature was already very close to what we wanted. So we just formulated a simple closed form expression based on this feature for the augmentation itself. Now, this functional form, what this does is it just says that, well, activate the augmentation only if it is above a threshold of 0.9. So C8R is essentially the threshold for my feature. And then the maximum value of my augmentation should not go above 5. That's what C beta max is. Now, once we did all of those things, we started testing it on various flows. And when we tested it on the 2D wall-mounted hump, what we found was that, well, the reattachment location shifted to the left, which was good. It actually slightly overcorrects, but that is what we have. And then for the separated region, we see that there is, discrepancy in the CF value. So where the SST and SA were calculated correctly, my new SST model, and by the way, the SLC stands for shear layer correction. So that new SST model actually gives you some error, but it essentially gives you the reattachment location correct. What you also see on the right is that the augmentation field now does not resemble anything at all which we saw for the SA inverse field, right? This just came about in the trial and error process, and it was working. So we did not want to just change it just to match what we have. It was something that worked, and we wanted to see how well it worked. So we just went ahead with this. Okay. Now the question was, is it doing what it is doing for the right reasons, right? So we checked the Reynolds stress profiles at different locations, and here I'm just showing one location, and we saw that yes, it was actually doing things for the right reasons. That is, the Reynolds stresses were increasing in areas where separated shear is. Okay, then we did the same thing for curved backstep. It is more or less the same story. You have the reattachment location corrected. You have some discrepancy within the separated regions. But yeah, that is what you have. What we also found was that this region, this dark red region, essentially, this almost does nothing because the kinetic energy the turbulence kinetic energy is too low and has more or less no effect. So basically, what is relevant is just this bottom part. Okay. Now, the 2D periodic Hill case is the same story. I would like to bring your focus to this reattachment location right here. It's about 5.5. The data gives you a reattachment location of about 4.5. I'll come back to this later. But essentially, yes, this is what the results are for the SST, the augmented SST model. Also, we did this analysis for the flat rate boundary layer just to see that nothing goes wrong for this. And while we see the augmentation getting activated in the outermost part of the boundary layer, things remain more or less nice in terms of the CF predictions. Okay. Now, this was an idea that actually Chris suggested. I was very apprehensive whether this would work or not, but Chris suggested that we should try the same kind of an augmentation function in the SA model as well. So what we did was we used the approximation for turbulence kinetic energy that is shown here, and we calculated REK, and we used the same augmentation for the SA model. And we are comparing whatever we get to another model in the literature, which is the rubber band model, which is also a pretty good augmented model. Okay. So surprisingly, it actually works well even for the SA. I did not think this would happen, but it did. So yeah. So what we see here is that, well, both the rubber band model in the literature and our model, they give more or less the same reattachment location. Our model does not give the same amount of skin friction recovery as the rubber band model, because our model was mainly tuned for reattachment, whereas the rubber band model was tuned for one or two more things. Both the models actually give you an increased turbulence stress, value. So yeah, and then the rubber band model for the curved backstep, it actually overcorrects a bit. Our model does not for this particular case, but yeah, that's essentially just a comparison. So it works for the curved backstep also in the Spalart-Allmaras model. Then for the periodic Hill case, both our model and the rubber band model are close. The rubber band model actually gives a reattachment. Our model does not for the Spalart-Allmaras model case, right? So remember in the SST model, our model was giving a reattachment at about x equals 5.5. In this case, it does not. So basically, things are not exactly identical across the SST and SA model. Our correction performs slightly well, I think, in the SST model scenario. Okay. For the zero pressure gradient update, our model was more or less very, very close to the original baseline SA model. The rubber band model showed a slight discrepancy, but I think that is within some error bounds. So that's all right. Yeah, and then there is the sharp backstep case. So remember, all of this we did for smooth body separation, right? And we did not account for sharp body separation at all. And we see the effects right here. So for the sharp body separation case, both our model and the rubber band model are off by quite a bit. Our model is actually off by more. So, but yeah, this is purely because this is a sharp geometry, and well, that is not what we did it for. But we would like to develop a limiter later to mitigate these effects for sharp geometry. Okay, so that was model performance. Now coming to some feature design pointers in a sense. So we tested a lot of different feature choices during this work. If you want to see an exhaustive list of features, then you can list the TM that we wrote in last October. Now, one thing that we noted was that different combinations of features can be used to create similar augmentations. And when I say similar augmentations, that means you see the same kind of improvement in the same general region in the field. And you can get that by using different combinations of features. So there's nothing unique about a given feature combination. All right. Yeah. Now, if you have a feature, as you might have noticed in the talk, if you vary even the functional form of that feature, right? In the sense that you use a log of Reynolds number instead of the Reynolds number itself, that may start giving you trouble. So one may be better than the other. And as I told you before, there is no automatic method right now to explore all the possibilities for these features. So the following slides, I'll illustrate these points with some examples. So the first thing is different functional forms, right? So if you take something as simple as the turbulence Reynolds number, and you have different functional forms of the same thing. Now, the fields look quite different, and that's important because what matters is the variation of the quantity, right? If the quantity is too low or too high, whether it is a machine learning model or a hand calibrated model, you'll find it very difficult to actually do something, have some variation in those areas. But if the feature itself has a good variation in an area, then the model has some room to breathe, right? So different functional forms of a quantity can be beneficial, exploring different functional form of the quantities. The second thing that I wanted to show was how different choices can affect what happens. So for example, the first figure, the top left, so the RET lim here is the limiter that I showed you before. Basically, model activates when RET is greater than 10, does not activate when it is less than 10, which is why you see, this is why you see such a sharp boundary right here. That is because of that limiter, the top sharp boundary. So basically, if you see something like R omega divided by R omega plus 3000, this is an arbitrary thing, right? You see a very nice hotspot right here for this flow, right? And we saw that we need our augmentation in this general region. So we could use this feature and get our augmentation using this feature. But the problem is that when you go to other flows, it does not generalize well because this feature, the value of this feature becomes Reynolds number dependent. So for example, if you go to very low Reynolds number flows, this may get the entire downstream field might get dark red. And basically your augmentation will start being applied everywhere. So you have to be very, very careful about what exactly you use for further flows. Then there's another feature you can use, which is basically a log-based feature, which I show right here. Now you can use this to create an augmentation, but what happens is in addition to taking effect in this region, the augmentation also starts taking effect somewhere upstream, because there is it's not shown here, but there's a blue region upstream. So that again is a big no-no. And then there's a similar story with regard to this feature for this feature as well. So basically, you can try several things, and look, all of these things have some kind of a distinction for that separated shear layer, but that does not mean that these will be good features.
Do you have some formal description what properties would you like? So that I guess you want to have changes, but you also want to have them local, right? So not
Right. So
it would help just to have.
So I have a bunch of properties in the TM that we drafted, but those properties are still like they're more or less guiding principles, because so guiding principles are there. That okay, it should be Reynolds number independent. It should be Galilean invariant. You should look for the bounds of the features. It's better if the features are bounded, right? So things like that. But yeah, other than that, this is why feature design is so complex, right? Because for every application, you'll have to do the process all over again. So yeah, that's essentially why this is kind of.
Yeah, but so that if you have this guidance principles kind of
right
defined universally, so that maybe you can at least a priori estimate which one is kind of satisfies those guidance principles.
So actually, even better than me, I think Dr. Philippe Spalart, he has a paper, and he has beautifully mentioned 20 different criteria. He calls them like strong. Gary, do you remember? Fallacies, right? It was fallacies, and also it was like philosophies. Yeah.
Fallacies is beautiful.
Yeah, so both. It has both. Yeah. So actually, Dr. Spalart's paper is amazing in that respect, because he tells us that okay, these are some things which are strong constraints, right? These 10 things are strong constraints. You have to abide by this. And then he also gives like 10 weak constraints. That okay, it'll be nice if you have this. And then I have my own views on some of those things, which I have in the TM. But I think people should read Dr. Spalart's paper on that.
Yeah. So it would be interesting to see the best choices for the cases that you have. How
right. So basically the feature choice that we showed in the beginning, right? That was the best that we got.
Okay.
After all the things, which is why it was in the main results. So this is basically just illustrating how difficult feature design process can be.
Yeah.
Right. At the end, by the way, this bottom right figure is an idea for people who want to do something more with this. I'll also work on this at some point. But this is a feature which is very interesting. It has the wall normal vector, which I know Dr. Spalart would not approve of very much, because for sharp geometry or for concave geometry, you can have a discontinuity in the normal direction. So that might be a slight issue, but what this feature does is it very well illustrates that separated region. It's extremely nice, right? So if somebody wants to go ahead with this, I'll also do something with this at some point. But this was an interesting find. So this is even in the TM, it is at the last. I just said that there's something interesting. People should look at this. Yeah.
So, now we are starting to flag that region, right?
Right.
But when you first started with the essay augmented model, you were flagging a region much downstream of that. And you went ahead with that.
Yeah.
Why?
Okay. Yeah. So when I started with that, this is a chronological thing. So when we saw this, right, we saw that we want to correct the CF values right here. And it made sense that we increase the turbulence stresses right there, right? And that is what we thought would happen, which is why we focused on that region. But once we got to this point, now at this point, we understood something even more fundamental. So the reason why, now you see, this is a very thin augmentation region. It's nowhere close to that region before, right? But it is sufficiently high that if a streamline goes through this region, it sufficiently bumps up the turbulence stresses such that they persist for quite a while, right? So that's a chronological thing, which I figured out later, not before. But this is.
So by the note,
Mhm.
for example, if that region slightly extended further than what you have,
Right.
because with the SA augmented, the new
Right, you don't
would it
have
get
the-
back that CF.
Yes, you could get back that CF, but you'll have to do a lot of back and forth of all of this, right? So it's very hard to get that right. But I think it can be done, but it'll take a lot of time. Okay, yeah. So in summary, essentially, yeah, we developed an SFT geometric evidence model augmentation that showed some good results, and it worked for flows beyond NASA wall-mounted hump, which was mainly used for the calibration. The baseline model was not significantly altered for attached flows. And by the way, we have more results on the attached flows in RTM. Basically, I think there are even some 3D cases on rubbing and things where it's clearly shown that nothing wonky happens with our model for those regions. And then the augmentation generalizes to the Spalart-Allmaras model as well. Now, this could indicate that there is something. There is a very clear efficiency in most turbulence models, which can be corrected for separated flows, and which is general across models. So yeah, that's just an idea. But I think that is exactly why the thing which I developed for SST also worked for SA. And then, yeah, these are the references, my SciTech paper from 2024 and the NASA TM that I wrote with my collaborators. Yeah, that's pretty much it.
I have plenty time for questions. Can I ask a question? I have a very basic clarifying question. I'm trying to understand what you're doing here. You showed the distribution of beta based on the optimization for given experimental data.
Right.
I thought you were trying to come up with a new turbulence model from these studies,
Right.
but probably that's not what you're trying to do.
No.
So for each new program,
Right.
you compute this beta,
Right.
but you need data, experimental data.
So not
What
for-
if you don't have experimental
right.
data?
So I'm not doing that for each new problem.
Mhm.
So it's like let's say I know that the turbulence model that I'm using, it lacks for separated flows, right? So I know and smooth body separated flows, let's say. So I know that my turbulence stresses are not picking up when the shear is separates. So what I need is one or two cases for which I have data. I use that data to create an augmented model. And now this augmented model is self-sufficient in the sense that you calculate features from within the solver, you feed it to the augmentation function, it gives you the values. Once you have that augmentation model inferred, right, then you can use it for unseen flows as well. Right, that is what I was showing, that well, I created this mainly using the 2D wall-mounted hump, but then it generalized well to other flows as well. For example, the curved backstep, which has similar things. There's a separated shear layer there as well. The periodic. Yeah, so basically it generalizes well.
So in this way, it is a new model in the sense.
Yeah, it is
Yeah.
it is kind of a new function added to a model.
Yeah, it's,
Like a low RE correction, for example.
it's a new model.
Yeah.
Except that you cannot write out like in
Um,
PDE.
For this case, you can.
But like in.
But in general, you cannot. Yeah, if you're using like a neural network, then you can't write it out.
Okay.
I mean, I think you can still write it out, but it'll be so long that nobody will use it.
Or like you
Yeah.
have to add physical insights to each scene.
Yeah, I think it's this machine learning stuff is useful to learn, and I always think that it would be nicer if we could learn from these results and then come up with some new turbulence model. Like, we missing
That is
this
exactly
term.
what I kind of
Right.
did here.
Yeah.
Yeah, but this is, I would say that in the literature of data-driven models, this is an exception. And I was very lucky that I came across this feature. It would very well have been possible that I might never find this feature before, right? And then I would have been stuck with a neural network. And that happens in a lot of cases.
Yeah.
But yeah.
How many features typically?
How many did I explore?
Oh, is it always one feature?
It's only one feature. That's the beauty of it. You don't need like 3 or 4 features. It's just one feature and it does job.
You don't need some combination of features.
Usually,
Yeah. I think if you have
so for complex,
some
Yeah.
neural network, you can find some right combination.
also like you could,
That-
if you want, you could break this into like 2 features, right? For example, you can say RE omega by REK to the power 0.61 as one feature, and RET by REK to the power 0.3 is another feature. So yeah, that way it's a bit ambiguous, but yeah, since we can write it in a closed form, so it's more or less one feature.
There's a question from online.
Yeah.
Go ahead, Cornelia.
Yes, hello, this is Cornelia Grabe from DLR. Yeah, thanks for the very nice talk. I have a number of questions, maybe very short ones. So first, the regularization that you used. So what was the typical lambda parameter that you used or that you came up with in the end?
So I think we used 1e-3 and 1e-4, if I remember correctly, for the regularization.
Okay. And
Like,
and
we tried everything between 1e-2 and 1e-5, and then we settled down to 1e-3 and 1e-4. That's what I would say.
And you used, if I understood this correctly, the experimental data as a reference, right? So from the green
Right.
blood, there are also a number. So there are also many DNS data, I think, available for this case. Were you also thinking in the beginning, maybe we should use DNS data because we have more data available there? And why did you decide in the end to use the experimental data as a reference?
So there are a bunch of reasons for that. One was that when we were starting out, then the only framework that we had at our hand was using surface quantities for to create the sparse function, right? So even if we had DNS data, we'd have to create, add to the framework for bulk quantities essentially to create a discrepancy and everything. And so that's one. And the other thing is that this field inversion kind of a thing was going on a bit before, since a bit before I joined. So I think Chris and Gary and Lee had a paper in 2023, right, Gary? Yeah, so around that time. So yeah, it was a matter of convenience, I would say, and also since we already had the experimental data at hand.
And they need to have confidence in DNS data.
Yeah.
And we had DNS data from skin friction, but this problem right here where you're trying to get the reattachment point correctly, there wasn't a lot of DNS that captured that at a reasonable Reynolds number. Just this experiment clearly shows it. And Chris had a history of wrestling with this issue for quite a while, so it seemed a reasonable choice to me.
Also, the pragmatic argument that at the end of the day, skin friction and pressures, surface pressures are what engineers care about.
Yeah.
Yeah, okay, I understand. Yeah, okay, thank you. And maybe one other question. So did you also take into account, let's say, other terms from, so you started with the SA model, that was my understanding. Right. For example, the relation between production and diffusion or something like that. Right. Was that also in your feature pool in the beginning and you find out that this wasn't meaningful enough?
So yes, the production development dissipation was there, the SW function was there. There were a bunch of other functions as well, which are there in the SA model. I would not go on to say that they are not meaningful because, as I said, there could be combinations which achieve the same, result. But this was what I found to work the best. I explored something about, I'd say more than 100 features, and their combinations. But yeah, this is what I found to work the best.
And just very short, maybe. So when you said you had roughly around 100 features, did you also test some, let's say, feature selection methods in a more automatic way? So I understand that you more or less manually looked into all these features, but there are some selection methods around, and for me, it would be very interesting to understand if something helpful also came out of these selection methods.
Right. So there is this tool called AutoSeeds, which we started using. So what that does is it gives you the best feature among a pool of feature, but that's limited to a linear regression kind of a thing. So basically you give it a beta, and then you give it a pool of features. It tries to give you the best kind of feature it can make out of those features to fit a linear model between the feature and the design. But that didn't help us much. However, one thing which I find very interesting recently is the information theoretic methods for feature selection. Now, I don't think these methods can be used to, create new functional forms out of features. For example, if you have something like RE omega and RET, right, and you want to go down to something like this RE omega to the power something, RET to the power something. There, I think you can use information theoretic frameworks to figure out what the exponents are very quickly. But going ahead and saying that RE omega and RET, some powers of this would be best. That, on the face of it, is hard, even with the information theoretic methods, just because there is such a huge pool of permutations and combinations that are there. I hope I get my point across. Like once you get your functional form correct, you can get the exponents right using the information theoretic method.
Yeah,
you can't do that before that. Yeah.
Yeah, thanks a lot.
Got a question following up on that one. So another thing you can do to try and tease out importance of features is you can use some sort of decision tree based model. Now I understand that there's lots of problems with this, but you can at least use it as a crude approximation to decide these features split your functional space well, these features don't split your functional space well. Have you explored doing that? Any decision tree based models?
So in my PhD, actually, I started with that.
Okay.
Yeah.
I assumed you.
No. But the thing with decision tree models is they're good on the face of it, right? If you have a lot of big data, these are really good models, really robust models, the decision tree models. The problem is that if you want to have something generalizable, then you only want that to take effect in regions where you want it to, and not touch anything else, right? A decision tree might not achieve that requirement, which is why I think, at least for the initial part of the feature design, a human has to be there, or at least maybe in a few years when AGI comes around, then maybe an AI can do this. But as of now, you need some physical intuition to know that, okay, if I use this particular quantity, it won't trigger anything anywhere else. It will only trigger things here in this particular vicinity. So for example, when I started to explore different features, RE omega immediately caught my eye, because for average pressure gradients and for separated flows, your maximum vorticity point lifts up from the wall, right? And as soon as that happens, your RE omega is immediately elevated. So that was a natural feature for me. But yeah, maybe a machine cannot understand that kind of requirement.
Great, thanks.
Yeah.
Dorul, go ahead.
Yeah. Hi, thank you, Vishal, for the very interesting presentation. I wanted to go back to fluid mechanics and the understanding of separated flows. This separated flow give birth to very complex phenomena that lead to highly anisotropic and inhomogeneous characteristics for turbulence. So maybe the Boussinesq approximation that we assume is not well suited or the best suited for this kind of flows, and maybe an enhancement of let's say the Reynolds stresses that we approximate to move away from Boussinesq is also needed. And I'm thinking about going back to Pope and his idea of expressing this Reynolds stresses more like a complex combination of this turbulence tensor basis and turbulence invariance, such that we incorporate more physics into our model. Of course, I mean, improving the turbulence models how they are today, and assuming Boussinesq approximation can lead to some improvement. There is a limit to that,
Right.
but including more physics into our model so it's kind of we try to reinvent. If we think about extending this way with the data-driven approach, we kind of try to come up with kind of like explicit algebraic models, but we invent them from data by optimization and field inversion, if you want. What do you think about that?
I think that idea has been very well explored in the literature. There have been a bunch of different algebraic RSM models, as you pointed out. And I think that idea has value. The only thing, so I haven't seen a convincing enough algebraic RSM model, a data-driven algebraic RSM model, which has both good convergence properties and gives you good benefits, which are generalizable. So on the face of it, I really like the idea. I completely agree with you. But yeah, I think more research is needed in that field. And yes, I agree. Like at some point, if resources and time permit me, I'd like to explore that.
Thank you. Any other questions? Yeah, but
Sure, if people have a chance. There's one online.
Chris.
Oh, hey. This isn't so much a question as a comment, but just to one thing regarding what was just asked a second ago is we have applied some full Reynolds stress models to this problem, standard ones, and they don't do any better than Boussinesq models. They still underpredict the Reynolds stresses in the shear layer and have too long a separation. And then just a note, interesting for everyone here, because some of you are aware of the high lift CRM work and how a lot of models are failing there, especially outboard, where they predict too much separation. They massively separate behind the slap, some of the slap brackets out there. And so we applied this fixed model, the SA version of it, to that case. And on the positive side, it didn't hurt, right? So it basically gave about the same answer, but on the negative side, it didn't help. So that's, which is interesting too, because it's kind of saying that the issue occurring on the high lift CRM outboard is not directly related to the physics that are happening in these 2D separation cases. It's maybe something else, or who knows? But it didn't make any difference.
Thanks, Chris.
Mm-hmm.
So, online, do you have any still question, Cornelia? Your hand is raised. And
Oh, sorry. No, I will
no. Okay.
put it down. Sorry.
Hey, Doru.
Yeah, an extra comment. So these Reynolds stress models also have closures that they have to be closed, right? And we cannot say that those are exact or necessarily apply optimally to any case out there. I see the possibility of enhancing those also with an approach like data-driven approach. So yeah, that was my comment. The fact that the Reynolds stress models failed for this case might not be surprising because they were not calibrated.
Right. No, that's a very good. That's a good point. Yeah. Of course, trying to fix those models may be a little more challenging.
Yes, I understand. Yes, agree. And that's why I think the intermediate, the step in between is figuring out maybe improving some form of explicit algebraic Reynolds stress models. Might be the first step.
Yep.
See, I've got a couple questions. So one is, so you can only, with your field inversion technique, tune a single functional beta, correct? If you were to try putting in multiple terms, that would then start breaking solution.
It wouldn't break it down, but there's okay. Let me actually say this. So I've tried in the past having multiple betas. So I did this for a transition model during my PhD. So I had a transition model, a bypass transition model for attached flows. So I had a beta, and then I had another beta sitting in front of that beta, right, which was for separated flows. So I know for a fact that hierarchically you can do this. You can tune model for a given flow phenomena, and once that is fixed, you can treat this model as a baseline model and add another beta, and then tune it for that. So hierarchically, yes, it can be done. I am not sure whether you can do it simultaneously because the two beta might interact with each other, and you can have more problems.
Physically, it may be a problem, but from optimization point of view, no.
Yeah, but it adds more non-uniqueness. There's already a lot of non-uniqueness in the field inversion.
But mathematically,
Mathematically,
there is no limitation in the number of parameters in your model.
Yeah.
As long as it's fine.
So another question I've had, and I've talked with Dorsani a little bit about this before, is so could you explore a flux function? Because I know there's some hand waviness about how, everything is just a right-hand side and it doesn't matter what we modify. From a conservative standpoint, there's a big difference between a source term and a flux.
Right. Also, I slightly differ from Professor Doraiswamy's position here. His analysis is correct that mathematically there's no difference, whatever you do on the right-hand side, right? But I feel that there is a difference in terms of the constraints that are implicit when you change a source term, compared to when you change a flux term, right? Mathematically, there is no difference at all, but constraint-wise, there is a difference. You change one thing that might not affect a given region in the flow.
Yeah.
But instead, if you change another thing, that might. So yeah. Now, as far as the flux function is concerned, I think that there already are some. There's already some work going on, especially for hypersonic flows, where people are exploring Prandtl number corrections. And I think that will count as flux function correction, right? Because it sits in the viscous flux term.
So as part, yeah, I guess they are using very similar techniques. Okay.
Yeah.
That's a good point, that the Prandtl number stuff is
flux correction.
Learning a flux.
Yeah.
Okay.
And discretely, there is a difference between source term and conservative limitations. That maybe there is no difference in terms of PDE.
Yeah.
It's all from particular grid, and if the difference may be very significant.
Yes.
And from iterative convergence point of view, actually to have conservation helps a lot.
Helps a lot. Yes, I agree. Yeah, but that is what I meant when I said constraints. You have different constraints with different terms.
Physically, what is the flux meaning then, like not apply here, because a lot of the turbulence activities are close to the cobalt dynamic, something flowing in doesn't mean it has to flow, it could get converted into source term.
Yeah, that was more a philosophical question. Here, where the Reynolds stress is too low, I don't know that changing fluxes is going to give you a higher Reynolds stress. I was more asking from a philosophical perspective. So another question is, so you spent a lot of time looking at a single test case. Have you also tried, hey, let's just take our beta, our input features and our beta across 3 or 4 different test cases, throw them all into a mix, then see what comes out the other side?
So the reason why I didn't do that was conscious. It was a conscious decision. And it was so because I already had a very few test cases at hand where smooth body separation is taking place in such kind of a 2D flow setting, right? So if I use a lot of those for training, then I don't have enough things for testing.
Oh, okay.
And basically, I don't want to do that kind of a thing, right? Where I say that, okay, I test something or I train something on a periodic hill at one Reynolds number and I predict another Reynolds number. I mean, while that has value, I think it has, what has more value is saying that, well, I didn't even see this geometry before, and I can still do some improvements.
Yeah, that's great insight. I do really like this. It seems like you're focusing on a lot of what would happen, and I'm thinking from the perspective of George Wang has been talking for 25 years about this slingshot effect.
Right.
How right around reattachment,
Right.
Reynolds stresses increase dramatically, and then they fall back to some sort of equilibrium level. It seems like this will start to capture some of that.
I'll tell you one more thing, actually, which is interesting. And so basically, the slingshot that happens physically is slower than the slingshot that is happening because of my augmentation. So my augmentation, which is a slight issue, my augmentation actually has a much faster slingshot effect. So you'll see the peak turbulence stresses actually occurring before the peak occurs in the physical turbulence stresses. So that slingshot effect is there. It's just that the speed at which it is occurring as you go downstream. Slightly there.
But that's cool that you're capturing some of that, because that's a kind of somewhat overlooked model failure that people say happens downstream of reattachment, so therefore it doesn't matter, but it is still a model failure.
Yeah.
And I know for where I'm concerned a lot of times about things like skin friction and heating downstream of reattachment. So I do care about what happens after reattachment.
Right. I mean, after reattachment, so obviously what is happening in the separated shear layer obviously affects some of what happens after reattachment. But then as you're focusing entirely on what is going to happen after reattachment, you also have to address that region as well, right, in terms of augmentations. So yeah, I haven't looked at that until now, but yeah, I'll have a look at that next year.
One last question.
Okay.
So when you showed the final essay of the Chris recommended augmentation, and you showed it for the flat plate, you still had the beta flag the edge of the boundary layer. Do you know?
For this, yeah. So basically,
you showed like all the beta functions for all the different cases. Yeah.
So I know why that is happening. So basically, at the edge of the boundary layer, the combination of features that I have, they actually exceed that critical value. The reason why that is because REK is sitting in the denominator. And REK, and basically I have two things, right? I have a filter on REK which says that if it goes below 10, switch this off, right? That switching off is not happening a bit above this. If I increase the threshold, if I increase the threshold, if I say switch it off below 20, you won't see this. But then you lose some of the other effects. It's a balancing game.
I assume production is also low there.
Yes. And I mean, since the kinetic energy, the turbulence kinetic energy is already very low, close to the edge of the boundary layer, this augmentation does not actually have a lot of effect, practically speaking.
Okay, thank you. I think at noon. So let's thank the speaker. Thank you everyone for joining the line and asking questions.